remember that Avogadro's number is the number of things that we have defined to be in a mole. Scientists have determined to be in a mole. This amount unit that we see in chemistry all the time. So we need to be able to use Avogadro's number to go back and forth between moles and number of things, and it can be anything. I mean, literally, it can be a mole of blueberries, and we know a mole of blueberries has a certain number of blueberries in it. That number of blueberries is Avogadro's number, 6.022 times 10 to the 23rd. You'll see it sometimes written as a capital N with a small a as a subscript, and it's 6.022 times 10 to the 23rd things in a mole. Things per mole. So, what we're talking about in this problem are carbon atoms. So if we have 1.187 moles of carbon atoms, so if we have this number of moles of carbon atom, how many carbon atoms must we have? Well, we would need some way or some number that we could use to convert between moles of carbon and the number of atoms of carbon. We said Avogadro's number tells us how many things are in one mole. That could be carbon atoms, that could be cars, that could be blueberries, that could be rainbows. You have a mole of rainbows, all right? But it tells us how many things are in one mole. So if I have 1 mole of carbon, the mole of carbon goes on the bottom, I wrote it there so that it crosses out, is how many atoms? Well, 6.022 times 10 to the 23rd atoms of carbon. All right, so it tells us how many things are in 1 mole. Now, let's contrast this to a dozen. Okay, so what if we had 1.187 dozen of carbon atoms? Well, I bet you all could tell me how many things are in a dozen. In 1 dozen of carbon atoms, there would be 12 atoms of carbon. This and this are exactly the same mechanism, exactly the same type of problem. Except we're not dealing with dozen, we're dealing with mole. Mole is exactly like a dozen. Except instead of it being 12 things in a dozen, it's 6.022 times 10 to the 23rd things in a mole. So if we look at it this way and we think of it as being analogous to a dozen, the calculation is actually not nearly as complex as sometimes students make it out to be. So all I have to do is do this calculation, plug it into my calculator, and I get 7.148 times 10 to the 23rd atoms of carbon. Four significant figures because I'm starting off with a number with 4 and I'm multiplying it by a number that has 4 significant figures, so my answer should have 4, which it does. Now, does this make any sense whatsoever? Does it make sense that this is 7.148 times 10 to the 23rd? Well, let's think about it. 1.187 moles is more than 1 mole of carbon atoms. If I had only 1 mole of carbon atoms, I would have 6.022 times 10 to the 23rd carbon atoms. That's what we use as our conversion factor. Because we have more moles than that, we have to have more atoms than that. So is this number greater than Avogadro's number? Indeed it is. It's greater by just a little bit more than Avogadro's number, because this number is just a little bit greater than 1. So our number does make sense based on what we know. So just looking at it, not knowing what the correct answer, you can sort of figure out sometimes what the answer should be. That idea that you can figure those things out and use those clues will come in handy on quizzes and exams as we move through this semester, and really for the rest of your life if you have that type of intuition and you can think about it in that way. So start to think about those types of questions. Does the answer that I have calculated actually make any sense? It will help you out in the long run.